All right, section 5.6, the law of cosines, starting on page 127 of your notes packet. We will start by defining the law of cosines. So in any triangle with angles A, B, and C, and opposite sides A, B, and C, similarly to what we were describing last section, notice the angles are still capital letters, the side lengths are still lowercase letters. The following equations are true. So we have three different equations for each of the different variables. We'll start by defining a squared equals b squared plus c squared minus 2 times b times c times cosine of angle A. Now, it starts out looking kind of like the Pythagorean theorem, but this is for any triangle. It doesn't have to be a right triangle, and that's why it is modified, where you have to subtract 2 times b times c times the cosine of A. We can also write a similar equation for each of the other two sides, so we can say b squared equals a squared plus c squared minus 2 times a times c times the cosine of b, and c squared equals b squared plus a squared minus 2ab cosine of c. All right, now each of these equations is actually the same equation because it doesn't really matter which variable we label each of these sides. Okay, so let's see how we can apply this. In example 1, we're looking at a triangle with A, B, and C, where the length of side A is 11, the length of side B is 5, and the length of, the angle C has 20-degree angle measure. Okay, so we are given side lengths A and B. We're looking for side length C, so we'll use the equation that solves for side length C. C squared equals a squared plus b squared minus 2ab cosine of c. And then we'll substitute in what we know. So c squared equals 11 squared plus 5 squared minus 2 times 11 times 5 times cosine of 20 degrees. Continue solving. C squared equals 121 plus 25 minus 110 cosine of 20 degrees. So C squared equals 146 minus 110 cosine of 20 degrees. We're looking for the value of C, so we can say C equals the square root of 146 minus 110 times the cosine of 20 degrees. Plugging that into a calculator, we'll find that C is approximately 6.53. So that's the length of side C. Now that we have all three side lengths and one angle measure, we can use either the law of cosines or the law of sines from the last section to calculate one of the other angle measures. So either way, I'm going to use the law of sines, and I'll say that sine of angle C, so sine of 20 degrees, divided by the measure of side C, 6.53, equals sine of angle A divided by 11. Solving for A, multiply 11 to both sides. We'll find that sine of A equals 11 times sine of 20 degrees divided by 6.53. Again, we need to use our inverse functions to solve this. So A equals sine inverse of 11 times sine of 20 degrees divided by 6.53, which using a calculator is approximately 144 144.80 degrees. So now we have that the measure of angle A is 144.80 degrees. We can use the angle sum of a triangle to calculate that 144.80 plus 20 degrees is 164.80 degrees. So what is remaining out of the 180 degrees is 15.20 degrees. So angle B has a measure of 15.20 degrees. So for our solution, we have that the measure of angle A is approximately 144.80 degrees. Side A has a measure of 11. Measure of angle B is approximately 15.20 degrees. Side B has a measure of 5. Measure of angle C is 20 degrees. Side C has a measure of approximately 6.53. All right, on the next page, looking at example 2, if we're given 3 side lengths of the triangle and no angles, we can still use the law of cosines. So we're looking at triangle A, B, C. Side length A is 9, side length B is 7, side length C is 5. So this time it doesn't matter which of the equations we use because we can solve for any of the angles at this point. So I'll choose angle B just for the fun of it. And we set up the equation 7 squared equals 5 squared plus 9 squared minus 2 times 5 times 9 times cosine of angle B. So I have 49 minus 25 minus 81 equals negative 90 times cosine of B. Dividing both sides by negative 90 and simplifying the left-hand side, I would find that cosine of angle B equals 57 over 90. Using an inverse of cosine, B equals cosine inverse of 57 over 90, which using a calculator is approximately 50.70 degrees. So that is the measure of angle B. Now from here we can use the law of cosines again, or we can use the law of sines. I prefer the law of sines, so we can set it up that sine of A divided by 9 equals sine of 50.70 degrees divided by 7. Solving for sine of A, multiply both sides by 9. Sine of A equals 9 times sine of 50.70 degrees divided by 7. Again, using inverse of sine, find that A equals sine inverse of 9 times sine of 50.70 degrees divided by 7. Using a calculator, this is approximately 95.74 degrees. So the measure of angle A is approximately 95.74 degrees. Now we can use the angle sum of a triangle. So 50.70 plus 95.74 gives us a sum of 146.44. So what remains of the 180 degrees is 33.56 degrees. So the measure of angle C is 33.56 degrees. All right, I've written all of the solutions in this triangle, but it's nice to rewrite them. So we will say A equals 95.74 degrees, B equals 50.70 degrees, C equals 33.56 degrees. Our side lengths A we're given is 9, B is 7, and C is 5 for the final solutions. Next, we'll look at using trigonometry to find the area of a triangle. So we can use the equation triangle area equals 1/2 BC times sine of A, which is also equivalent to 1/2 AC times sine of B, or 1/2 AB times sine of C. All right, this is very similar to the area of a triangle that you might know, except now we're not necessarily using perpendicular sides. We're using that factor of sine of the angle to compensate for if the sides are not perpendicular. So let's look at how this would work in example 3. Find the area of a regular octagon, 8 equal sides with 8 equal angles, inscribed inside of a circle of radius 9. So we have a circle whose radius is 9, and inside of this circle is an octagon. Eight sides. 8 sides of equal length, which means that inside of this circle have 8 equal angles. So a full circle is 360 degrees. Divided by 8 is 45 degrees, which means each of these triangles here has the side lengths of 9 and the angle of 45 degrees. Using the equation above, we can find that the area of each triangle equals 1/2 times 9 times 9 times sine of 45 degrees, which is 1/2 times 81, times the square root of 2 over 2 from our unit circle. So each triangle has an area of 81 times the square root of 2 divided by 4. And we don't have units here, so this is units squared, or square units. But it's asking for the area of the entire octagon, so now we have to take 8 times the triangle area, which equals 8 times 81 times the square root of 2 divided by 4. Thinking of this as 8 over 1 times the area of the triangle, we can reduce to get a total of 162 times the square root of 2, which is approximately 229.10 square units. All right, looking at the next page, we'll start by defining Heron's formula. Let A, B, and C be the sides of triangle ABC, and S denote the semi-perimeter. Semi-perimeter is the sum of the sides divided by 2, so it's half of the perimeter, and we call that S. Then the area of triangle ABC is given by area equals the square root of S times S minus A times S minus B times the quantity of S minus C. So this is another way to find area of a triangle. So let's look at example 4. In example 4, we're finding the area of a triangle with sides 13, 15, and 18. So let's create our triangle here. 13, 15, and 18. So our semi-perimeter is 13 plus 15 plus 18, all divided by 2, which gives us 46 divided by 2. So S equals 23. Then our area equals the square root of 23 times 23 minus 13 times the quantity of 23 minus 15 times the quantity of 23 minus 18. So that gives us the square root of 23 times 10 times 8 times 5, which gives us the square root of 9,200. This can be simplified to 20 times the square root of 23, which using a calculator gives us an approximation of 96 square units. Example 5 uses the law of cosines in a word problem. Once you've completed that, go ahead and reflect on what you've learned this lesson and write your summary in the box provided on the next page.